Hi guys, today's lesson is all about how to find an exact value of a trig ratio. So we're going to develop some special triangles that will allow us to come up with the exact value instead of having those ugly decimals like sine theta equals 0.4237921 or something like that. Instead we're going to have things, ratios that use roots and other type of fractions, okay? So something like root 2 is an exact value. It means the square root of 2. Now, if you put root 2 into your calculator, you'll get 1.41214, which is actually an approximation because they're rounding this irrational number of root 2. So we like exactness in math as much as possible, so we want to be able to come up with ways where we can write just root 2 instead of having to write the decimal. So we can use special triangles to determine the exact value of sine, cos, and tan of these angles. 0, 30, 45, 60, and 90 degrees. These are special angles. So recall that the length of a line does not actually change the value of an angle or its trig ratios. So for example, if you have this angle here, theta, it doesn't matter if the line ends here, or if it ends here, or if this line ends here, or it's extended to be all the way here. It doesn't matter how long these lines are, that doesn't affect the size of that angle. So that's just something to keep in mind. And because it doesn't affect the size of the angle, it doesn't affect the size of how big sine, cos, and tan are either. So let's just look at 0 and 90 degrees, okay? So if we draw 0 degrees, that's just this here, right? That is 0 degrees. If we draw 90 degrees, that's on this arm here. That's 90 degrees. Okay? That's a right angle. So remember that on the Cartesian plane, sine theta is y over r, cos theta is x over r, and tan theta is y over x. Or you can think about it as the slope. So since the length of the radius doesn't matter for these things, like we just talked about, as you go around the circle, let's just let the radius be 1 because that's the simplest we can let it be. Can't let it be 0 because you can't divide by 0, and you can't have a radius of 0. That doesn't make sense. So 1 is the simplest. So then, sine just becomes y divided by 1, which is just y. Cos becomes x over 1, which is just x. And tan theta stays the same, y over x. So if this radius is only 1 unit long, then this would terminate at point 1, 0. Okay? So then that would mean that the sine of 0 degrees is just, remember it's the y value, so it's just equal to 0. So it's equal to y, which in this case is 0. Cos of 0 degrees is equal to x, which in this case is equal to 1. And the tan of 0 degrees, which is equal to y over x, so we can think about it as slope, would be 0. 0 divided by 1, or think about it, the horizontal line has a slope of 0. So there we go. Now you can use your calculator and push in sine 0, cos 0, tan 0. You'll see these are the answers that you get. Okay? Now for 90 degrees, again, if the radius, if this is 1 unit long, then that means x is 0. It hasn't moved left or right, but we've gone up 1, so the y value is 1. So if we look at the sine of 90 degrees now, that's y, so in that case it's 1. The cos of 90 degrees, which is the x value of this point, is 0. And what about the tangent, though, of 90 degrees? That would be 1 divided by 0, which is undefined. Okay? Also, you can think about it again as the slope. The slope of a vertical line is undefined. So there you go. All of those terminate on the axes, okay? So you can think about, you can reason the sine, cos, and tan in all those cases by just letting the radius be 1 and then thinking about what the coordinate would be. Okay, you could continue this to do 180 degrees. So So the coordinate here then would be -1, 0. And you could continue this to 270 degrees. This coordinate here would be 0, -1. So you could come up with your sine, cos, and tan using the same method by just labeling a coordinate on the axis, the simplest coordinate. Now think about it. If you had let your radius be 3 or something, then that means that this coordinate would be 0, 3. So sine would still be, sine would still be 1 because your y value would be 3, but your radius would also be 3. So 3 over 3 is 1. So no matter what you make the radius, the ratio stays the same. So we just make the radius 1 so that it's easiest to deal with. Okay, so that's dealing with 0 and 90 degrees. But what about primary trig ratios of 45 degrees? So the first thing you want to do is create a right isosceles triangle. So pay careful attention at how this triangle is created, because it's best to memorize how to create the triangle rather than just memorizing the triangle. So it's a right isosceles triangle. So that means that these two are the same length, these two sides. And so that means that those two angles have to be equal. So because they're equal and it's a right triangle, that means out of 180 degrees, 90 is already taken up. So therefore you have 90 left to distribute evenly amongst those two corners. So therefore they each must be 45 degrees, okay? Because you have 180 total in a triangle, you take away the right angle, divide it by 2, and you're left with 45 degrees. So I'm going to let each side equal 1. Now remember, it doesn't matter. I could make them both 2, I could make them both 10, I could make them both 17.345. It wouldn't matter. So I'm just picking the simplest side length of 1. So if those side lengths are 1, then the hypotenuse is equal to the square root of 1 squared plus 1 squared. That's just Pythagorean theorem. So it's equal to root 2. So that side is equal to root 2. Okay? So sine of 45 degrees is opposite over hypotenuse, so it's 1 over root 2. Okay? So if you find the sine of 45 degrees in your calculator, you'll get some gross decimal. Okay? Blah, 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 blah. If you put 1 over root 2 in your calculator, you should get the same gross decimal. Okay? But 1 over root 2 is obviously a lot nicer than that gross decimal. It's an exact value. Okay, the cos of 45 degrees is also 1 over root 2. And then the tan of 45 degrees is opposite over adjacent, so that's just 1 over 1, which is just 1. Now, I should mention to you here that another way of writing 1 over root 2 is you do something called rationalizing the denominator. Now, this is important because in math, sometimes we don't like to have a square root on the bottom on the denominator of a fraction. So if we multiply by root 2 over root 2, we're really just multiplying by 1. Root 2 over root 2 is just 1. So we're not changing how big it is. But then you're getting root 2 on the top, and root 2 times root 2 is just 2 on the bottom. So in some mathematics, root 2 over 2 is preferable to writing 1 divided by root 2. Okay, it's just kind of like writing 2 over 4 or 1 over 2. Okay, to get from 1 over 2 to 2 over 4, you just multiply by 2 over 2, which isn't changing the value of it. It's just multiplying it by 1 to get to that. So these mean the same thing, they just look slightly different. Same thing with this. So 1 over root 2, I will accept that as an answer. But in the back of the book, you might see something like root 2 over 2. That is the same number. Okay? So that is just being multiplied by 1. Okay. All right, so that's 45 degrees. So you need to know that special triangle and these ratios. So now we'll get on to 60 degrees and 30 degrees. So I've created here for you an equilateral triangle, okay? But you should highlight just half of the equilateral triangle because that's what we'll be looking at. So in an equilateral triangle, the 180 degrees are divided evenly. So this would be 60 degrees, and this would be 60 degrees here. So this whole thing would be 60 degrees, but half of it would be 30 degrees. Okay? Now, usually we want to make our side lengths as simple as possible. So you might say you want to make this 1, 1, and 1, but then half of 1 would be a half, and we don't want a fraction. So we're going to make the side lengths 2. So this would be 2. We don't really need that. But this little section here is 1. Okay, so then we need to label the length of this height here. So using SOHCAHTOA, we find that it's root 3. Sorry, not SOHCAHTOA, Pythagorean theorem. Okay, because it's it's the square root of 2 squared minus 1 squared, which is the square root of 3. That's how we got that, just Pythagorean theorem. There's a little thinking bubble. That's how we got that. So we know that the ratio of these sides is going to be 1 to root 3 to 2. So therefore, the sine of 60 degrees is going to be opposite over hypotenuse. So root 3 over 2. Okay? The cos of 60 degrees is 1 over 2, adjacent over hypotenuse. Okay? And the tan of 60 degrees is root 3 over 1. So root 3. Okay, so no matter how long these sides are, that will always be the ratio of the sides. So it'll be a 1 to, if this is 60 degrees, this side to this side will always be a 1 to 2 ratio. That's what that's saying. So the sine of 30 degrees then is 1 over 2. The cos of 30 degrees is root 3 over 2. And the tangent of 30 degrees is 1 over root 3. Now again, you'll notice this pesky little radical in the denominator. So again, they might rationalize the denominator by multiplying by root 3 over root 3, which gives you root 3 divided by 3, since root 3 times root 3 is just 3. So this is just another way of writing 1 over root 3. So you might see this, root 3 over 3, or you might see 1 over root 3. It's the same number, you're just writing it in a different way. Okay, so you need to understand how this special triangle was created, and then after you've created the special triangle, how you come up with those trig ratios. Okay, now we have a few more bits of useful information before we get on to our examples. So this is kind of a review from earlier. The trig ratio of any angle is equal to the plus or minus of the trig ratio of its related acute angle. So here I labeled, you can draw this too, 135 degrees, and its related acute angle is 45 degrees. So that means that the sine of 135 degrees is equal to the sine of its related acute angle, 45 degrees. Okay? The cos of 135 degrees is equal to the negative sine of 45 degrees. Okay, that's because cos of 135 degrees, because it's in quadrant 2, will be negative, so we have to take negative sine 45 degrees to make that negative. Okay, and the tangent of 135 degrees will be equal to, now think, is it positive or negative, of tan of 45? Well, normally tan is positive, obviously, but in that quadrant it's negative, so then we have to make that negative. Okay? So sine of 45 degrees is 1 over root 2. So the sine of 135 degrees, because it has a related acute angle that is from one of our special triangles, we can use that special triangle to come up with 1 over root 2 as the sine of 135 degrees. So cos of 135 degrees is just negative whatever the sine, sorry, that should say cos. Negative whatever the cos of 45 degrees is. So that's going to be negative 1 over root 2. and this will be -1 because the tan of 45 degrees is 1, so the tan of 135 degrees will be -1. So you use the related acute angle to find the value of the ratio, and then you use which quadrant it's in to tell me if it's positive or negative. I'll say that one more time. You use the related acute angle and its associated special triangle to come up with the value of the sine, cos, or tan ratio, but then you use its position in the Cartesian plane to come up with whether that value should be negative or positive. Okay? And the CAST rule will tell you if it should be positive or negative, right? So this is CAST, tells you where the ratios are positive, or you can use logic. Sine is related to cos. Sine is related to whether x is positive or negative. Sine is related to whether y is positive or negative. Cos is related to whether x is positive or negative. And tan is related to whether slope is positive or negative. So here's another little example. If you have the sine of 210 degrees, well, its related acute angle here is 30 degrees, okay? Because it's 180. To get from 180 to 210, that's an extra 30, right? So that's equal to the negative sine of its related acute angle, because sine in this quadrant is negative. So if you go back up there, the sine of 30 degrees is 1/2, but I need to make it negative because it's in that quadrant. Okay? So the cos of 210 degrees is equal to the negative cos, it's negative because cos is negative there, of 30 degrees. So I go back up there. The cos of 30 degrees is √3/2, but I'm making it negative because of the quadrant it's in. And then the tan of 210 degrees, tan is positive there, so it's just the tan of 30 degrees. And that is 1/√3, or √3/3. And just a reminder as you're doing these exercises that if you have the root of something multiplied, so root x times root x is just x, okay? So √3 times √3 is just 3, √10 times √10 is just 10. All right, so that's most of in developing the information you need to do these examples. So now let's actually do a few examples. So example 1, determine the exact value of sine 45, cos 45, plus sine 60, cos 30. So I like to, when I'm using my special angles, I like to just create the special triangles on the side to refer to. So this is my 1/√2 and 45 degrees in either corner. You just have to draw it in one. Then I draw my half equilateral. So this was 2, this is half of 2, so it's 1. That's √3. This was from the original equilateral, so it's 60 degrees. This is half of the original angle, so it's 30 degrees. So when I have my special triangles drawn there, I can easily refer to them when I'm looking for the sine, cos, or tan of any of those angles. So sine of 45 degrees is just 1/√2. So instead of sine 45, I write 1/√2. Now instead of cos of 45 degrees, I again write 1/√2. Plus the sine of 60 degrees, so here's 60, so √3/2. And then the cos of 30, so that's also √3/2. Okay, so now I want to simplify this. So I just use BEDMAS. So I do my multiplication first. So this is just multiplying fractions. So 1 times 1 is 1. √2 times √2 is 2. √3 times √3 is 3. 2 times 2 is 4. So I just end up with a half times a quarter. So this is just 2/4 plus 3/4. So I actually just end up with 5/4. And there you go. Okay, now I'm asking you to come up with the exact value of these angles. So you'll say, Mrs. Weens, you must have made a mistake. There's a 0 in there. That's supposed to be 45 degrees. Because I know 45 degrees is from a special triangle, but 405 degrees isn't. Well, I didn't make a mistake. 405 degrees, of course, is not from a special triangle. But if I'm asking you to find the exact value of something, that should be a big ding, ding, ding in your head that this angle given must have a related acute angle that's either 45 degrees, 30 degrees, or 60 degrees. Because it's not just 45, 30, and 60 that you can find exact values for. It's any angle that has 30, 60, or 45 as their related acute angle. Then you can find the exact value for their trig ratios. So the first thing you want to do is place this terminal arm in the proper quadrant. So 405 degrees, that's one whole revolution around to 360, and then another 45 left. So in fact, it terminates here. So you've gone all the way around to 360, and then again, so this is 405 degrees. And then you want to label the related acute angle, which is 45 degrees. Okay? So the cos of 405 then is going to be equal to the cos of 45 degrees, which is just 1 over root 2. Okay? And I know that it's positive because it terminates in quadrant 1 and cos is positive there. Now what about the tan of negative 240 degrees? So let's find out what quadrant that terminates in. So negative is going this way. So I have negative 90, negative 180, negative 270. So it has to be in this quadrant, okay, between negative 180 and negative 270. So draw the arrow to show that it terminates and it's going in that direction. So then I label my related acute angle. Okay, so this was negative 180. So that means there's 60 degrees left between the x-axis and that terminal arm. So label it as positive 60 because the related acute angle is always positive. So the tan of 240 degrees will be relative to the tan of 60. So the tan of 60 degrees, ooh, I gotta remember my special triangle, so I quickly just draw my special triangle. Here was 60, this is 1, 2, root 3, so I have root 3 over 2. So therefore, the tan of negative 240 degrees is root 3 over 2, but it ends in quadrant 2, so it's the negative version, so it's negative root 3 over 2. Now be careful, this ratio is negative because it terminates in quadrant 2, and tan is negative in that quadrant. It is not negative because the angle is negative. You could have a negative angle that terminates here, for instance. Like this would be a negative angle, but it would have a positive tan ratio because tan is positive in quadrant 3. So this is not negative because this is negative. It's negative because it terminates in quadrant 2. So the key idea of all of this is